Good, a warm welcome to all participants of the Faculty Development Program on Smart Building Design towards Net. And we are honored to welcome Dr. Kishor S, Senior Scientist at Central Building Research Institute, Roorkee, as our esteemed expert speaker for today's sessions. Dr. Kulkarni brings extensive experience in the field of the building science, particularly in the thermal performance assessments and energy efficiency enhancements. So today he will be speaking on the topic of thermal monitoring and energy efficiency in the buildings, which is highly relevant as per we move towards the designing smart, energy conscious and net zero environmental buildings. So his insights will help us to understand how to evaluate, optimize and improve thermal comfort and energy use in both existing and new structures. Now I call Shubham Meena sir to briefly introduce our expert to the participants. Shubham Meena sir.
Thank you, Ravi sir. And hello. Just give me a minute. There is some kind of discrepancy. Is it fine? Hello. Yeah. Thank you, Ravi sir, and good afternoon, everyone. We are honored to welcome Dr. Kulkarni, a senior scientist and assistant professor at the Central Building Research Institute, Roorkee. Dr. Kulkarni holds a PhD in civil engineering from NIT K Surathkal and ME in civil structures and BE in civil engineering from Shivaji University, Kolhapur, with expertise in civil structure and building energy efficiency. His research encompasses areas such as industrialized building systems, concrete technology, concrete structure, building physics and thermal comfort, building ventilations, life cycle assessment, building retrofitting, low energy and buildings, building information modeling. Dr. Kulkarni has organized and contributed to numerous workshops and training programs. He also significantly contributes to sustainable habitat development, climate responsive architecture, and building science and technology advancement. Please join me in welcome.
Thank you, Shubham sir, for nicely introducing our participants. Once again, we warmly welcome you, sir, and we extend a warm welcome and looking forward to an over to you, Kulkarni sir.
Thank you very much. May I audible? Yes. Okay. Thank you. And first of all, I am thankful to Ravi sir, Meena sir for inviting us. Particularly from CBRI, another two speakers also spoke in this particular development program, and so I am thankful to them, and also I am thankful for introduction, for the nice introduction. So as suggested, so I have made my so let me share my screen first. Can you able to see my screen?
Not yet, sir.
Okay.
Sir.
Please check now.
Yes, sir. Now it's
Okay, it is in full screen mode.
yes, sir.
Okay, thank you. Slides are also moving.
Yes. Fine.
Okay, thank you. So let me start with my presentation. The presentation topic is that is temperature monitoring and energy efficiency in building. So maybe you are aware with the CBRI. CBRI is a institute which is under CSIR, and CSIR is the Council of Scientific and Industrial Research, which is established way before independence. And CBRI is established, that is Central for Building Research Institute, which is established in 1951. So we do work in different areas. Our vision is to provide the solutions in the building construction, habitat planning, and the construction. Our focus R&D areas, which are that is architecture planning and energy efficient building designs. That is our one of the area. Apart from that, we do work in advanced materials, disaster mitigation, health monitoring, and modeling and simulations. We are having here 8 R&D divisions, which includes architecture planning and energy efficiency, building materials and environmental sustainability, construction automation, robotics, fire safety engineering, geotechnical engineering, hazards, heritage and spatial structures, and structural engineering. So as of you aware, we are facing a lot of challenges as on today, and there are certain issues. The challenges are with respect to the some of the natural resources which are getting depleted. So we are facing crisis on that one, and also this is because of the some the man-made disasters. Because of that one, we are facing this problem, and as we can say, the climate change is the biggest issue, and this is because of the some of the factors such as that is a greenhouse gas emissions and other things. So if we see the greenhouse house emissions, the major contribution in this is carbon dioxide, which is 77%. There are certain other greenhouse gases are there where contribution is very less, but and the impact may be more with respect to other gases, but the majority share lies with the carbon dioxide. So people are more focused on the carbon dioxide and carbon dioxide related industries, how we can able to reduce the emissions. And if we see in case of the buildings, there are two major sectors. One is the cement industry, another is the steel industry, which are producing a huge amount of the CO2 emissions. And in case of the building, if we consider through building also, there is a greenhouse gases which are getting formed, not directly but indirectly by the usage of electricity and the heat. If we do design buildings properly, then we can reduce this the CO2 emissions. And for that, the today's topic, that is what the energy efficient building designs, and the particularly this particular FDP program, which is on the net zero energy building, which is much more important. So if you can see here, buildings, maybe residential commercial buildings, almost 15% of CO2 emission which is coming from this, 25% almost electricity and heat altogether. So for that purpose, we have to consider how we can able to reduce the CO2 emissions. And for that, this particular building designs are very much important. And for this, there are certain commitments also made by the Indian government under the COP26, and wherein five Panchamritas that we have considered. And with respect to that, we are changing our policies, we are doing research, and we are creating the innovative technologies wherein we can able to reduce the CO2. Otherwise, we can utilize that generated CO2 in maybe different utilization areas, and through that we can able to reduce. So under this, the one of this prime goal, that is by 2070, our building should be net zero carbon emission building. So that means
This is
that
the
whatever the
bulb.
materials we are
और बंदेगा ऐसे, ठीक है, बता. Sunny Dog.
so with respect to this, if we consider this net zero carbon emission buildings, that means whatever materials what we are consuming, obviously there will be embodied carbon which is associated with that, but through the renewable energy sources or to other things, we can able to compensate that one. And during our operational, because one is buildings before construction, there will be some embodied energy. During the operational phase, we are utilizing the heat, and if we do the calculations of this carbon emissions, generally it is observed that 70% of the energy we do use during the operational phases. That means if we consider the lifetime of building is 100 years or 80 years, then in that case we do consume energy, and that creating a bigger impact rather than the building materials what we are using. So for that purpose, the building designs are very much important, and for that only there are certain philosophies and the principles that we need to consider. And for that there are certain sustainable development goals are there. And particularly if we see the building industry or the our construction industry, there are certain roles wherein CBRI plays a major role, that is affordable and clean energy, clean water and sanitation, industry innovation and infrastructure, because infrastructure is one of the biggest pillar, sustainable cities and communities, so and the climate action wherein CBRI role is there. And with respect to this, there are certain areas wherein the new innovations are being considered, and in that R&D activities are undergoing at the CBRI. So that may be a carbon neutral material wherein how we can reduce the embodied carbon, how we can utilize the material by using the CO2 emissions. So the other things, innovation in the architecture planning, climate intelligence and integration, how we can able to collect the data, futuristic data, and we can create the algorithms, and with respect to that we can design that buildings, innovation in the materials, and there may be the smart materials, bio-based solutions or self-healing structures, energy efficient system, that is maybe passive design principles, or by integrating the renewable energy sources, resilient infrastructure, so wherein CBRI is contributing. So coming to the topic of the today's presentations, so first we should understand building, and there is a heat which is getting transferred in the building, and that phenomena that is generally taken with respect to three things, that is a conduction, convection and convection. These are the heat transfer things. The conduction, as we are aware that the heat is getting transferred through these solid things, and without any motion of the material, solid through the solid particles, the heat is getting transferred, but the material will not move, that is stable. So the rate of heat transfer, which depends on the what kind of temperature gradient is there, and the properties of that particular material, that may be a specific heat property, thermal conductivity property, and based on that one, this particular conduction and the speed that matters. Obviously from higher to lower, temperature is always low. The another phenomena is the convection. Convection, that is what there is a mass motion of the fluids. That means the best example, if we can heat our the water, so with that we can able to feel that there is a movement of this fluid. That means when that particular mass of the water is heated, then it is getting circulated, it comes up, there is a circulation. So this particular phenomena consider convection, and for this the windows wherein through air is getting circulated, air is getting ventilated, so through that also it comes with the heat that is getting transferred from inside to outside or outside to inside based on the climatic conditions. So this is one thing. And the third thing, as the phenomena, that is the radiation, that is what it is, the emission of the electromagnetic wave which carry the energy away from the emitting object. So here in case of the building, if we see, then the solar is the source of energy, and through the solar radiations, that these radiations which are coming inside the building, and through that we can heat is getting transferred. So that is what the radiation is. So if we consider all together these three phenomena, that is heat flow through building envelopes, there is a certain heat which is getting transferred inside to outside or outside to inside through the conduction, through the radiation, through the convection, and there may be some mechanical devices through that also. Suppose for example our computers are there, office equipments are there, or any other equipments are there, that also generates the heat. Otherwise evaporation also, through that this heat is getting taken away. So if we see the building, there is all this phenomena is taking place. And if we see the heat flow part, that is what, as we know that the heat is getting transferred from the higher gradient to the lower gradient. So that heat flow, which is not a steady state, which may be transit, but we should understand what is steady state and what is the transit. In the case of the steady state, temperature is constant at any time. Generally, this is not the real condition, but if we assume that temperature is outside is constant and continuously that much heat is getting transferred, or inside temperature is constant, if we are maintaining the room temperature maybe 27 degrees centigrade, then in that case that 27 degrees centigrade, and outside is if it is less, then obviously it is the temperature which is constantly going out. So another, that is a transit or the conduction, that is maybe dynamic or non-steady. If you can see, this is what really we are close to this particular, because the India comes under the tropical, and wherein our buildings are natural ventilated. That means outside temperature is getting vary, inside temperature is also getting vary. But if we see this particular diagram, the outside temperature may be higher at one particular time, wherein inside temperature may be higher at different point of time. So it is not like that when the outside temperature is maximum, that time only inside temperature is maximum. It is not like that, because heat transfer, it is happen with respect to the time period. So there is a time is the another dimension which is there. So here in this time lag, that we can call it, where the difference between T outside maximum temperature to the inside temperature maximum, so that particular difference which is considered as a time lag. And there is some the factors, other factors are also associated. So so if we consider this particular wall envelope, wherein the heat is getting transferred from maybe outside to inside, and wherein, as we know that solar radiation, there are this the long wave radiation, short wave radiations, so that are incident on the wall envelope, and through that the wall is getting heated, and through conduction the heat is getting transferred. So if you see the heat flow path, there is a conduction. If we consider there is a steady state conduction or maybe a dynamic state of conduction. So in case of the steady state, wherein we look for the building properties, that is U value is the one of the property of the envelope. Through that we can able to calculate what is that particular heat flow, or what is the quantity of heat which is getting transferred inside to outside or outside to inside. The another one is the dynamic, which is based with respect to time, and there are certain numerical things are there. Through that we can able to find out finite difference or finite element methods. Otherwise also response functions are there, that time domain or frequency domain. Through that we can able to calculate. With respect to today's presentation, we are just touching the steady state, how the steady state heat flow which is taking place. So for that one particular typical, if we consider heat conduction through a plane wall, where is the outside temperature is higher, and from higher to the lower, that is TO, that is outside, T1 is the inside one. So there is a L is the thickness of the wall envelope, A is the cross sectional area, K is the property of that material, which is known as the thermal conductivity. How much the thermal conductance of that particular material is there. So that based on that one, there is a certain heat transfer phenomena. Suppose for example steel is there. Through steel the conduction is taking rapidly as compared to the other materials. So because that is one of the reason is that thermal conductivity, that means maybe it is associated with the density of that particular mass, it is associated with the properties of that particular material. So otherwise if we consider this stone rod and maybe a steel rod. Stone rod where the conduction which is not as fast as the steel one. So this is what the difference between T naught and T Z, that is what we consider a difference, delta T. And alpha is again the thermal diffusivity, because the surface properties also plays an important role. For example, in case of the surface properties, you may be aware of that perfectly black body and white body. White, it is a reflecting, that is a property of that particular paint, or maybe the radiations based on that one. That is what the material property. So wherein in case of the black body, it will absorb that particular heat. So if we consider this Fourier-Poet's equation, because heat is coming through all three directions, maybe X, Y, Z, that means maybe two directions, and maybe from bottom or from the top. So if we consider this is an equation, general heat conduction equation, and if we consider the one-dimensional state system wherein only we are taking considering to one dimension, then delta T by delta T is considered to be 0, and then no heat generation, that Q by A. If the heat generation also we are considering as 0, then in that case this equation we can able to consider that other two dimensions also we neglect, and only X direction if we consider. And if we do integrate, there will be we get the constant C1 and C2. And if we do calculate, if we put the boundary conditions at because at X is 0, for example, at this particular time, 1 is X is considered to be 0, and 2 is X is considered that is with respect to the with respect to the length. X is equal to at L, T is equal to T1 and T is equal to T0, that is outside and inside temperature. And if you put these boundary conditions into these equations, obviously we can get an equation which shows that temperature varies linearly with the X direction. If we put in that, and if we do the calculations, then this equation that is what tells that temperature varies linearly with respect to S. That means it is a steady state. And another thing is that temperature distribution is independent of K, because in this particular equation, in the previous equation, if we see, there is no K which is there in this particular equation. So it is independent of the thermal conductivity, temperature distribution. So if we can put from Fourier's law of heat conduction, and if we put this our particularly this T in this particular equation, and if we do differentiate, then obviously we get the equation that is Q is equal to minus Ka T1 minus T naught divided by L. And if we put the value of your K by L as a thermal transmittance, then this equation is simple as Q is equal to A into this delta T. So with this, we can able to find out, we can able to get that what is the heat transfer is there in this particular wall. So for example, but we know that walls are not made up of only single material. Walls generally made with the different materials. So outside layer may be plastered with the cement plaster, inside layer with the plastered with the cement plaster and putty as well. So in this case, if we see the different layers having different physical properties, there may be different thermal conductivities. So if we want to calculate the what is the heat flow, then each layer we have to consider, and through each layer we can, if we do calculate, then we can get this kind of equations where the property of building that resists that particular is considered as the resistance, thermal resistance of that particular wall envelope. So layers may be included, or insulation if we can use, or cavity, that is also considered the kind of insulation only. So if we put all together, then we can get some equation like this, and wherein we can see that thermal gradient through the cross section of wall. So at last we can get Q is equal to UA delta T. So this is what the equation. With this we can able to get the steady heat flow. And based on this steady heat flow, we generally do calculate that how much mechanical devices we need to put inside so that we can get the thermal comfort. So this is what the basic basis in order to calculate what is the heat load. For that, we have to provide the mechanical solutions like air conditions. So again, for different wall having different areas, that all together we can calculate, then we can get one particular heat flow value. So there is a internal external temperature that is also there. And if we consider that one is a outside temperature measurement line is there, one is inside temperature measurement line is there, and that two horizontal lines, straight lines, which are the steady, that are the mean temperature, then in this case we can able to write this T outside air temperature with respect to T, that is the mean of the outside air temperature and the fluctuation. Because if we consider that mean line and over and above and bottom of that particular temperature line, there are certain fluctuations, so that can be rewritten like this. So so based on this, we do calculate what is that the heat flow for the unsteady state. For this particular presentation, we have restricted this steady state only in order to understand how this particular heat transfer phenomenon is taking place and how we can able to calculate the heat load, and how these material properties are important, what are the different layers, and through that how it is matter that how much heat is coming at what particular time period. So obviously that is a U value is generally a value which is considered for the steady state, because it comprises of the all the values. Maybe the surface resistance also it is taken care, the different layers of the wall also it taken care, and the insulations or the cavities, that is also it is taken care by under this particular thermal transmittance. So and for this particularly the unsteady part, there are certain things are there through that we can able to calculate. So as I'm talking about the different thermal parameters, that is what the parameters, thermal conductivity is the one parameter, and the last one is the thermal transmittance, that is a U value. So in between there are certain definitions are there which are associated with the properties of that particular material. So how much the resistivity of that, how much conduction, conductance is there, resistance is there, and the specific. These are the certain physical terms are there which are associated with the material properties. The general unit for the transmittance, that is W per meter square into K. So that's why this Q is equal to UA into delta T. So with this we can able to, Q is measured in terms of watt, so that we can able to get it. So in our CBRI, we do have this hot girdle plate apparatus wherein we can able to measure the thermal conductivity of different materials. Different materials we can able to measure. For example, in order to understand the conductance, if we can see the 100 mm brick and 150 mm concrete, if it is there, the thermal conductivity of both the materials is totally different. As we are aware that we don't feel comfortable in the concrete houses if our walls are also concrete, roof is concrete, and other our floorings are also concrete, then obviously we feel for example when we go during the daytime, if we are outside and all this building your doors and windows are closed, then when we return at maybe 5 o'clock 6 o'clock to the home, then we feel that even outside temperature is less, but inside temperature is huge. That means because of this thermal values, so conductivity values and the time lag, so we are we are uh, we are getting the difference in the temperatures. So for example, resistance, if we put the values, and the resistance of brick value is more as compared to the concrete value, even though the thickness is less. So that is what different layer have different resistance values. So effect of radiation, that is also another thing. As I mentioned, there are three things are there. One is the conduction, convection, and radiation. So that again depends on the what is the heat absorbed is there, and the example is perfectly black body. Black materials will absorb more heat, wherein in case of the white, which is transfer that heat. So in case of the unsteady, these are the diagrams of B, C, and E. Due to the heat storage capacity of material, unsteady flow occurs. There may be different layers of material having different heat storage capacities. So obviously light wall having a different behavior, whereas in case of the heavy wall having a different behavior. So because of this, the low and high thermal mass, the time lag, if the high thermal mass is there, then in that case, obviously the time lag will be more. If the thermal mass is less one, if the thickness is less, then obviously time lag will be less. So these are the certain equations are there. With this, we can able to calculate the time lag. So the thermal loss, because if we can provide the building with only the insulation, also will not able to solve this our purpose, because we are we have to provide this both thermal mass as well as insulation. So our wall element should consist everything, not only insulation, not only thermal mass. So if we can put more thermal mass, obviously we can increase the time lag. So if our this earlier buildings, if you can see, the wall thickness was huge. That means they used to make up to 600 wall thickness, so that they are restricting this heat entry through the time lag process. So as soon as that heat is coming inside, the time lag they are increasing in such a way that, so during the late night hours, uh, that heat can enter into building. But by that time, if you can open windows and through cross ventilation, natural ventilation, obviously heat is taken out. So not during the peak time. The high density material like concrete, bricks, tiles require great deal to heat energy change. But at the same time, if we can provide very less thickness of this particular concrete and other things, then obviously the time lag will be less. Then through this heat will come inside. So the thermal performance of any particular envelope depends on the effect of radiation on the opaque surface. That is also we should consider the absorptivity, long wave emissivity, that are also important, because the radiation, that solar temperature, other things do play here major role. And sequence of layers does not influence the steady flow to and may have the effect of periodic heat flow. So the third is convection, that is a ventilation heat exchange. So for the ventilation also, if we can say see the equation, and this equation, with this we can able to find out that how many number of air changes required, and if that much changes are there, how much heat is coming. So that we can able to find out with respect to the ventilation heat exchange. So I have not taken details of this one. So just to introduce, so I have taken a little bit. So for this radiation also, this particular Q is equal to IAW with this, because how much area of window is the main source, through which window or maybe door opening, if it is open, through that radiation is coming inside. So through that we can able to calculate what is the intensity of radiation. Obviously the radiation intensity may be high at the peak hours, and for that solar path diagram plays an important role. And through solar path diagram we can able to find out the orientation of the building, and which is the opening which is subjected to heat entry. So that kind of thing we can able to calculate through this. So as I mentioned, that thermal thermal transmittance, which is related to steady state flow, and where in case of thermal admittance, this is related to the unsteady. So the thermal performance of the walls and roofs can be measured with two parameters, that is insulations and thermal mass, and thermal transmittance, that is what steady, as I mentioned, thermal transmittance, which is related to the steady state, and admittance, which is related to the unsteady. So amount of energy which is leaving from internal surface of the element into the room per unit degree of temperature swing, that is nothing but the definition of this particular admittance. So that, as I mentioned, that example of the fluctuation, that is mean temperature, and what is that fluctuation is there, and that fluctuation we can able to calculate with this the admittance parameter. So if we want to reduce the loads, that is either heating load or cooling load, then in case of the thermal transmittance, we have to consider as low as possible, and the thermal transmittance we can consider as high as possible. So with this, if we understand this, with this we can able to reduce this heating and cooling. So this is what the first part of my presentation, which is on the heat flow through building envelope. The another part, because one is the building envelope features and how these are behaving. There is one feature. Another is the climatology, because all this together depends on the climate, what kind of climate outside is there, and based on that how our building is performing. And generally buildings are we do construct the buildings in order to get the thermal comfort inside the building. So that is what our main functionality, apart from maybe strength, and it again protects against the disaster, that is the thing. But also at the same time we do construct buildings in order to get the thermal comfort, and thermal comfort that is necessary to create the indoor thermal comfortable environment, so that people can work, people can take a rest, and so that people can relax. So that for that purpose, thermal comfort we have to maintain, and thermal comfort depends on the various factors. The maybe which is related to what kind of activity we are doing, what kind of clothing we have put in, or maybe other reasons. But with respect to the building, if we consider, then this is depends on the what kind of envelope that we have put, what kind of openings that we have given. So for in order to measure this thermal comfort, so there are certain indices are there, so which through which we can able to uh, uh, measure that the thermal comfort, because thermal comfort is not only depends on only the air temperature, but also it depends on the what kind of humidity is there. Also it maybe depends on the what kind of air circulation, air movement is there. So in order to take care of this all this parameter, there is one particular indices is there, that is effective temperature. These are the old indices. Temperature which is this effective temperature, wherein as per a definition, temperature of the still saturated air which has a some general effect. So that is what your the effective temperature, and wherein these are considered temperature, wind, and humidity. If we consider this particular Indian climate, wherein at different point of time we even though temperature is same, but we feel different things. So for example, in case of the coastal, even though temperature is less, but because of the humidity in the air, we don't feel comfortable. Where at the same time we may feel comfortable on the seashore, where if the wind is flowing. So because of the wind also, that is creating another the sensation, thermal sensation, to which we can feel. So this what the one indices, effective temperature. There are so many indices are there, and as far as uh, India concerned, we have developed, CBRI has developed tropical summer index. That is what our thermal index is. So there are other like PME PPD is there, WGBT is there. So there are some astrobate, some of the nowadays people have done adaptive base also. So this tropical summer index, which is developed by the CBRI and which is being incorporated in the SP41 code, wherein this particular tropical summer index which given. So this is as per as definition concerned, it is defined as the temperature of the kame at 50% of the humidity, which imparts some thermal sensation as the given environment. And as we can see that when we are there inside the building, and if we are not feeling the comfortable with the natural things, then we switch on the fan. So with respect to the air circulations, we feel comfortable. That means air circulation, what it do, it is reducing the thermal sensation. That means it will decrease the PSI values. So for example, 0.5 airspeed is there, there is a decrease of 1.4 degree. And this is what the equation with which we can able to measure that PSI. And if we take a, if we plot on the psychometric chart these values, herein you can see the black one, where is the initial the relative humidity 30 to 90%, 30 to 70%, and where is the temperature. This is a particular line of tropical summer from 25 to 30. Under this, there are certain black areas there that is considerably comfortable. Otherwise, any point which is coming outside this one, then at that particular point we don't feel is a comfortable. So this particular range is given as 25 to 30 as a comfortable temperature, and the optimum condition is 27.5 degrees centigrade. So below 25 or above 31, we generally do not feel comfortable. So there may be the uncomfortable starts at that particular time. And again, below 18 degrees centigrade or 20 degrees centigrade, we feel very cold kind of thing. So some kind of tolerable cool up to 19 to 25, below 19, and that is too cool, non-tolerable kind of thing. Then in that case, we have to depend on other things. So these climatic conditions, as I mentioned in the psychometric chart, so that can be posed, and we can able to get season wise the comfort chart. So for example, here in warm and humid season, and the dry season, hot and dry season, and the cold season, that are being uh, placed here. If the temperature and the humidity, based on that one, we can able to see. So for this, how we can able to make our building as a thermal comfort? So obviously there are certain passive design strategies through which we can able to reduce the temperature. And these passive design strategies, that is nothing but the layout plans are there, building materials are there, orientation is there, and other shading devices are there. So all that, if we can plan in advance, then we can able to create our house as a good house, thermally comfortable house. And if it is thermally comfortable, then obviously your load which is there on the mechanical means, that will be reduced drastically, and your house will be efficient, energy efficient house. So now again, then how to design these buildings? And for building designs, whether comfort is the criteria that we have to consider, or something else that we need to consider. So with respect to that, we should understand the climate and the climatic classifications. Climate is nothing but the average condition of the atmosphere near the Earth's surface over the period of years. And where is in the climatic classification, that is one nothing but the formalization of the system that recognize, clarify, and simplify the climatic similarity. That means where the climatic similarity is there, that is considered to be a one particular climatic zone map. So difference between geographic areas, and so this climatic classification is very much important. We can enhance our scientific understanding on the climate also, can be increased by the climatic classification. So in India, if we can consider, there are certainly 5 climatic zones are there at present as per as the code concern. So climatic classification, generally people do, agricultures also do, marine engineers also do, and the transport industry, other industry they do. So their application is totally different. And if it comes to the building design, the climatic classification, what is done, so that is totally different. So these two things are different. So most important that we have to consider where we have to design that building, and for that what is the extent of temperature with which this building is exposed to, and based on we need to design. So climate, in that case, climatic zoning is very much important. So what are the parameters generally world over? If we see in order to do the climatic classification, as we know that India is a diversified country wherein different states are there, and at every maybe we cannot say exactly, but maybe every 10 kilometer or so, the culture, the housing typologies, other our food habits, everything changes here. So we are having different cultures, different these climatic conditions, and for that we our all that houses are we need to design. So other factors also generally considered, that is solar radiation, precipitation, but these are not much influencing the building designs. So the two things which influence it, that is temperature and the humidity, that are the major one. So there are certain climatic classification which is done by the different. There may be genetic base and empirical base, wherein in case of the empirical, we required that all that data, temperature, humidity, precipitation, all that data is required, and based on that only we can able to do it. So Copenhagen is the first one who started the classification based on the empirical data. Earlier to that, the climatic classification happens to be based on the genetic base, that is the natural laws of the climate formation, based on that one it used to. So the first climatic classification which is done based on this particular um, thing, that is empirical base, that is Copen one, and this Copen is considered to be a bliss climatic classification. And the other, after the Copen, whosoever comes, they have followed this Copen classification, and they have added some subclimatic zones with respect to the Copen only. So Copen classification, Copen has worked 1900 to 1940, and he proposed some climatic classification. Later on, the different scientists across the different countries have worked together. The Köppen classification, there are certain 5 broad climatic groups are there. That is tropical, arid, mesothermal, microthermal, and the polar one. And these are the 5 main classification. After that one, they are again subdivided with respect to 5. And in order to set the criteria for this 5, there are certain criteria. That is, the winterless climate is considered to be tropical. Dry, which is the climate where evaporation exceeds the precipitation, that is what they consider a arid one. And the mesothermal or mid latitude, that is based on the humid and middle thing, that is latitude, and mild winters, severe winters is the microthermal. And the polar one, and that is the average temperature of the warmest month is itself is below 10 degrees centigrade. So he is the Köppen. Later on, he has used this Köppen, and he again revisited, and then he has revised. He has added some kind of seasonal distribution parameters, temperature parameters, and some other parameters. Based on, he has again revised that one. So if you see this Köppen at present throughout the world, this is what generally it looks 1951 based on that one. Then after that one, again they have done work, and Köppen is another scientist. He has worked. He has presented also same thing. The other scientists they have also work here. but the Köppen is considered to be the base one. So as we know that there is a climate shift is taking place, and based on that climate shift, there is certain changes are taking place. So this particular map, which is taken the climate data from 2001 to 2025, and based on that one, this is the climatic classification. There is a shift is taking place. If you can see this, there are changes in the temperature. So obviously now because of this the climate change, we know that temperature are getting increased, and we are not able to restrict that 1.5 degrees centigrade temperature restriction. So that is what our worry is. So there is a shift in the temperature, and if we consider the futuristic, then we can compare this both the maps, and we can able to see how this climate is changing and color shading is also getting changed. The climate change phenomena is generally not to be considered as a new phenomena. It generally used to have this particular change, but the way with intensity it is happening, that is what a really concern for all of us. So this is particularly old map of this India, wherein this for the building applications they have considered temperature and humidity, and based on that one they have proposed 4 climatic zones. And then again our the scientists from CBRI, they have again worked and in 90s 80s, and they have come up with the initially 6 and later on they come up with the 5. So these are the 5, and wherein the 5th group, which is made in such way that applies to where the 6 or more month their temperature is the constant or stable one. So that is considered to be composite. So these are the criteria are there. So monthly maximum temperature, relative humidity. Based on that one, we can able to segregate the things. So the composite, that is what more than 6 months only one temperature is there. So no, more than 6 months there is variation within that. There will be variation. Suppose for example, if you consider Delhi as an example, after every 2 months their temperature is changing, and for that purpose it is considered to be a composite one. So after that one, this particular scientist of CBRI work, and then 2005 they have proposed this particular 5 climatic zones. Later on we have again because climate is changing, climate changes are observed, so we are again revisited, and generally we have based on different particular methodology, we have again classified our Indian zone map, and which is put forward to the BIS. Now the committee is formed, and based on that committee recommendation in future, this particular map again it will be revised, and new map will add in the BIS code. So there are certain methods for this climatic classification. One may be degree days, cluster analysis, administrative boundaries, that district administrative boundaries are there. Based on that one, we can decide. But India is, as I mentioned, the diversified country. The climate is diversified. Everything is diversified. So here, based on administrative boundary, we cannot able to make it. Bioclimatic things, building and solutions. So these are the things based on that one. Generally, classification is done. So if you can see this particular chart, wherein even though India having a huge land, but we are having very limited, and some of the countries which are having not that much land, but they are having the number of climatic zones are different, more also. So the climatic zonation is classified based on the purpose, that is performance based, perspective based, passive design guideline. So based on that one, we can able to classify the zones. So in our research, what we have used is hierarchical cluster analysis we have used, and based on that one, we have proposed some kind of climatic zonation. So there are certain methodology steps are there that I will skip here. So cluster, as we know that there are certain things which are common, similar, and that is considered the one particular cluster. So that means the points which are nearer to that one, that are grouped together in a one, and then those are far away, that are grouped separately. like that it is considered the cluster zonation. So also at the end we can get with this cluster zonation we can get the dendrogram, so with which we can able to make it the number of different groups which comes under one category. So you can make it from this particular diagram. So here we have used the hierarchical cluster analysis, and wherein we have gathered more than 350 stations, and we have collected all that 350 station data, and based on that one we have done the clustering analysis, and we have proposed some kind of climatic classifications. So in order to do what we have done is, after taken that data, we have checked for the any missing things are there, that we have again rectified, and then we have done through the ArcGIS, and through ArcGIS. Before that one, we have done the cluster analysis, principal components we have done, and based on that clear clustering analysis, and based on the GIS, we have mapped the climatic zonation on the India's map. So there, during this process, there are certain statistical analysis we need to do, and this statistical analysis with which that data is getting filtered, and we can get some meaningful data. So these are the some distance and the things are there. So with which also we can able to make it. So here is D1, D2 consider one particular thing group together. Then the next nearest number is 3. So it is made a group in that way. So as I mentioned, this we have used certain things, and I will take you directly to the research outcome. So we have considered the 81 to 2010, that is 400 meteorological data, and based on that one, this is what the classification which is being proposed. So these are the some of the results of the climatic classification. So the climatic classifications, what we have done here is based on the cluster analysis, and after that one we have considered some kind of prototype building, and this particular base model we have considered in the different climatic conditions, and through that simulations we have identified the same building, same envelope, if we can use in the different places, then obviously their performance is different. For example, here Jaisalmer, where energy requirement is huge, because the cooling load is more. Uh, similarly, in case of the requirement of heating, there are certain buildings which required the heating as well in the particular month of December and the January. So some of the outside agencies like building the Bureau of Energy Efficiency, they have rated based on the what is the energy consumption. Obviously, we have to design our buildings in order to reduce the energy. That is what our main, and that can be done through the passive strategies or maybe active strategies. In case of active, we have to utilize the renewable, but as far as possible, we have to reduce the energy consumption. That is what is very much important. And the climate and body heat loss, that is also having a relationship. For example, hot and dry, the human body which loses the heat by evaporation and perspiration, this perspiration from the skin. So for example, here in suppose for example we are feeling heat, and if there is a sweating through that also, body obviously heat, body is not taking the time, that means storing the heat. Obviously, in order to make body as a comfortable and the constant temperature, obviously that particular natural phenomenon taken place. And in fact, in our building also we use the coolers, evaporative coolers, so that through that we can able to make ourselves as a comfortable. So similarly, in case of the hot and dry, wherein the humidity is not there, wherein through the humidifier we can able to provide the humidity. So in case of warm humidity, we have to dehumidify. So through the convection barrier, if we can provide the air circulation, then we can, in case of warm humid climate, we feel a little bit comfortable. Temperate climate, wherein body loses the heat uh, through the all possible modes, heat loss, and the cold one, wherein we have to conserve that the heat we need to conserve against the excessive rate of heat loss. Suppose if we put the data of the weather data on the psychometric chart, and here the yellow boundaries which tells the thermal comfort criteria, and this particular dotted points which are behind this whatever our the comfort criteria, TSI, comfort criteria, thermal comfort indices. So, so for this, obviously, we need to design accordingly. We need to provide the design strategies, passive design strategies as well as active design strategies. So similarly, Kolkata, there may be certain points which are there under this particular comfort boundary. So what is required in case of the whenever we have to design the warm and humid, for example, coastal areas, then there we have to reduce the internal heat gain. The heat which is coming outside to inside, we have to reduce. That we can relocate the kitchen well apart from the living areas where the kitchen is producing the heat, so that we can take to uh, the the outside or away from this living areas, by providing roof O-ring so that we can cut down the solar radiations. And as we may be knowing that thermal bridging, because if the chajjas are getting heated and these chajjas transfer the heat inside the building, because chajja is a member which is connected with the internal surface inside, and through because daytime the chajjas are getting heated up, and that is this particular heat is being transferred. Increase the heat loss. Heat loss also we need to increase, so that for that we can able to ventilate our courtyards, windows, openings below the roof, placing the bedrooms in the south to receive the maximum wind. So that can be done. Reduction in the heat transmission, that can be done so through the insulation that can be providing, and we can reduce that. And the humidity control, so obviously humidity plays a major role in case of warm things, by absorbing and deabsorbing the earthen walls, wherein dehumidifier we can able to make it. So these are the typical examples of the areas where this particular warm and humid temperature is there. Obviously, if we see this kind of traditional buildings, obviously these passive strategies are being implemented there. And if we consider this modern RCC building, wherein they don't take care of all these things, the rainfall is there. That's why slopey roofs are there, and these particular tiles are there, which is made up of the locally available material. So itself, this itself as a it is nature based adaptive kind of materials and solutions. So in case of the hot and dry, wherein we if you can see the Jaisalmer, there are certain points which are there in the comfort zone, but there are points which are extreme, far away from this particular comfort zone. And these are the peak points wherein high the energy demand, in order to make it building as a cooler, make it building as a heater as well. If you can see this particular data which is segregated, which is the extreme cold is there, extreme heat is there. So in this case, we have to reduce the solar heat gain. And how we can able to do, we can able to properly orient our building. Orientation, that smaller walls we can provide towards the east west. Row houses can be made so that shadows come to the other houses, and we can reduce this minimum wall area also. Overhang roofs, large trees, and we can avoid the openings. Massive structures can be made. If we consider this example of Jaisalmer, Rajasthan region, wherein if you see their walls are constructed with the the heavy thermal mass, that is the mud walls they do consider, and the stones, because stones having a high this energy storage capacity, you can say. So that are also being used in case of the this hot and dry climate area. Increase the heat loss, that we can able to increase the heat loss through evaporative cooling, and also we can put the courtyards, ventilations uh, to the west side, or sprinkle the water system, through that we can able to, and balance the temperature fluctuations. So in case of the Rajasthan, Jaipur, if you go, there are certain gel mahals are there, or maybe artificial ponds are there, and through which only that evaporation is taking place, and evaporative cooling effect we can get it. So balance the temperature fluctuation. So temperature fluctuation, that means we have to increase the time, like so during the night only that heat should come inside, so that through ventilation effect we can able to minimize it. So in case of a cold climate, that is Srinagar is the example, the data point which is lies in the colder region, and here we have to harness the solar radiation. So that's why the longer walls which we do face on the north side, so that we can harness the solar radiations, and the south side, which is no, we don't put any windows there, so that we can obstruct the heat loss, that is decrease the heat loss is the another thing, and wherein we can provide the false ceiling, we can avoid the openings, windows areas, window size we can reduce it, the height of the building that can be reduced, and the small doors openings that we can able to give, and we can increase the internal heat gain as well. So that can be done with we can place the kitchen below, in even though people are not accepting this, uh, uh, but uh, but if you want to make our building as a climate responsive, climate resilient, then in that case these are the passive features which need to be implemented. So this is a typical example of the Leh Palace, which is more than 300, 400 years old. And if you can see, the main thing, these walls are made up with the locally available material as a material. And these walls are thick ones, 600 thick. So which obviously makes the building as a comfortable. So coming to the last part of my presentation, that is what the thermal monitoring in the buildings. So passive features, that is the what we need to consider. The materials which we are developing, that are the energy efficient materials. For example, the example brick. Generally, we do use bricks, but the modern materials like AEC blocks. AEC blocks lightweight in nature, and there are certain advantages with respect to this particular block, because as it is a lightweight, obviously there are certain pores which are there inside this particular AEC block, and because of that one we can get little bit comfort, we can avoid the unwanted heat entry inside the building. So for that purpose, what we have done here, how much that quantification is important, and thermal monitoring is in that sense it is much more important. So in order to do this, there are certain instrumentations which are required. So some, this pyrometer, that is the first instrument which is required in order to capture these solar radiations. Data acquisition system, so through sensor we can capture heat stress, that we can able to calculate what is the TSI, or tropical summer index, what is that the globe temperature, that can be done. So flow for the flow meter purpose, anemometer is there. And as I mentioned, there are different indices are there. Thermal comfort indices. One of the indices is predictive mean over or PPD. So that is can also be measured. And U value, that thermal transference, and our elbow diameter thermal U value, that gives the temperature difference and the heat flux. And with this we can able to calculate, that is the thermal transfer. And algorimeter, wherein solar radiations can be measured, and the the uh, radiated waves are there, radiated things are there, that also being captured from the bottom bulb. So in our CBRI, we are having a prototype building, and we do experiment on these buildings. These buildings are made up of the different wall materials. One particular left side you can see that is made up of the brick wall, and the other which is considered as a AC. And with we have done the measurements on this. So what we have done, also we have measured the U values. What we have done here, that we have put the sensors in this particular buildings, and which are through this our data acquisition system we do have monitored. So similarly, this is one particular prefabricated building which is made up of the 3S system, wherein columns and beams and slabs are RCC, and wherein envelope material which is made of the AAC. And the thickness of this brick wall is 230, and this particular AAC is 150 mm wall. So if we consider the U value, obviously 150 the U value is 0.62, and wherein in case of the brick the U value is 2.17. Obviously U value is more. So these are the other dimensions what is there, and this is the IoT place we have developed, and this is what the building. So rooms we have placed the sensors outside and inside at the same location, so that we can able to capture the what is that fluctuation is there. As I mentioned, some of the parameter load, your time lag is there, decrement factor is there, all that we have measured in this particular building. And as far as the Roorkee, this is what the solar chart, which is the solar chart for Roorkee for this particular latitude and longitude. And obviously here during the peak winter only, we don't have solar radiations for 1 or 2 months. Otherwise, there will be solar radiations, and obviously these things are important in order to design the buildings. So here in our another lab is there, CSIO. With them we have measured the temperature, and there are certain things wherein accuracy of these sensors we need to check it, calibration we need to do it, and RTD sensors we have used here. RTD sensors which are having capacity up to 250 degrees centigrade that are being used here, and humidities are also used. Some other sensors like lux sensor is there, heat flux is there, that are also used. So so this the data what we have captured through this. In a building we have put almost more than 30 number of sensors, and we have monitored outside inside temperature variation during all the season almost. For one week in different seasons we do have monitored the data, and this data which can give us the insight of the performance of this particular newer materials which are being used in the building nowadays. So as we can see here in temperature monitoring, we have done surface temperature monitoring, and wherein we have put the sensors through all the sides. That may be a south side, that may be the west side, east side, north side, everywhere. Roof also we have put the sensors. Almost we have put more than 50 sensors, and we got the interesting things. So considering the south wall and the west wall, obviously evening time the sun goes to the west side, and there we got the more temperature, and there is obviously difference in the temperature inside and outside temperature. Time lag also in case of the west, time lag is less as compared to the east side. Similarly, with respect to the south, we got the time lag as a 5 hours, whereas in case of the north, we got the time lag as a 3 hours. So definitely there is a performance change is there, and this we can able to observe through this performance monitoring. And the temperature of the roof, obviously roof, because most of the times roof is obviously exposed to the solar radiations, and obviously always capturing the heat and transferring to the bottom. So roof temperature generally goes more than 58 degrees centigrade or 60 degrees centigrade. So, and if we consider building designs, the larger part of heat which comes through the roof only, and also the maximum portion of heat loss also taking place through the roofs. So almost 45% of the heat loss which is taking from the roof. So that people nowadays people are aware and people are using this cool roofing solutions over the roofs. So sometimes they put the glazed tiles or the mosaic tiles. Earlier we used to insulate with the brick pat coba or maybe mud. We used to put on the roofs and we used to insulate it. So now technologies are changing and newer materials are coming. So based on that one, new things are available in the market, and that can be picked based on the area and the climate, the climatic variations in that particular area. Based on that only we can able to provide the solutions. So similarly, this is the AEC block for the different regions, because throughout the year we have measured. So here in case of the Roorkee, we can get the peak temperatures during the May or maybe June, and then before peak summer, what are the temperature after peak winter, before peak summer. So that kind of measurements we have done, and we do have monitored for consecutively 7 days continuously, and based on that we got the interesting things, and these are being analyzed. uh, so analyze, and based on that one we can make the calculation how much the wall thickness we can able to provide, and what is the AC wall performance, what is the performance of the brick wall. So that things we can able to make a comment on that one. So this is a compressive one particular chart is there wherein maximum minimum temperature is mentioned. uh, so the surface temperature time lag is also mentioned, and based on that one the other parameters like time lag decrement factors can be calculated. So obviously, the building wall performance, there are certain TPI values are there, thermal performance index values, and this is nothing but TIS minus 30 degree divided by 100 into 100 divided by 8. That 8 is considered to be 8-hour time period, and 30 is the best temperature is considered. And based on that one, TPI values of the wall envelopes can be given some kind of gradings. So that may be good, power, bad, that kind of ratings can be given. So this particular table, earlier table, which it shows for the south and north, this particular table shows for the east and west. So obviously AEC block here we have used 200. So particularly on that peak days, these are not providing a satisfactory results. So if we can see values, only if we consider the during the peak winter and during the peak summer, the values, the quality of this envelope is not sufficient. The performance is poor. That means there is certain things which need to be taken care. So that kind of comment we can able to get it. And also the thermal comfort, other, as I mentioned, that not only depends on the only one temperature, but also other factors also considered. That is radiant temperature, air speed, humidity. So that all things need to be considered. So herein, this is a one particular building wherein we do have monitored this thermal performance through that one instrument, Delta OM thermal comfort meter is there. Through that we have measured, and these are giving these are these values of the PMV for that particular room. And if we see that the percentage of dissatisfaction, people's percentage dissatisfaction is there, that we can able to make it through this particular graphs. So there are certain 3-4 rooms are there. For 3-4 rooms we have measured out this different temperature. Moreover, if you can see this graph, outside temperature is more and inside temperature is less. That means there is a little bit the comfortness is there inside this house. So at last, the conclusion that in our CBRI we are having all kind of setup in order to do the measurement, real-time measurements. Also, we can able to change the envelope. Simpod facility is available at CBRI. That Simpod consists of the wall envelope, that is the frame envelope, wherein we can able to cast the anything, and then we can able to test in that particular building. So that is what the test bed setup, wherein we can get exact idea how these new technologies are performing to our the climatic conditions. So to conclude this, it can be summarized that climatic types are important components in the sustainable building design, in the energy efficient building design. The climate that we need to understand for which the building is designed. So based on that one, the availability of material, locally available material, other things we need to consider. And as we know that there are certain restrictions are there with respect to the availability of the space, and with respect to the availability of the materials as well, and availability of the skills. Based on that one, we have to provide the solutions, keeping that into mind that the climate is the main parameter, and based on climate we need to design it. So this is what buildings must be designed to fit in which they are built in which the climate. So that's why uh, the climatic zones are important, and based on that one we need to design. So that's all from my side. So I hope I have covered the things that are assigned to me. So over to you. If at all anything questions are there, anything is there, that I will be happy to answer it.
Sir, that you said 400 station weather data is collected to make the zones of climate in India. So do you have the list in the map list or any table list?
Yes. So, as I mentioned, we have collected from the across 400, more than 400 that data points we have considered. And for that, one particular IMD climatological normals are there, and that from that IMD only we have collected. So, if you want that particular data point name that I can share to you, that are across the only one particular drawback in that only the part which is the Jammu Kashmir part, upper part, maybe Leh part, or maybe Arunachal Pradesh. Therein we don't have any IMD station points, so there little bit data is missing. Otherwise, almost in the all the different states that the data is covered, and that data is available with us.
Actually, I was worried on the zoning exact at the border of this zoning, like which stations you considered, especially in, what humid, warm and humid, and this uh, temperate zones near Bangalore.
Okay. So, for example, if we can see that IMD, they are having a these IMD stations near to airport, or maybe some strategic location. They are having some IMD stations, and they have provided IMD station based on the requirements. The one particular station, how much area is captured. Based on that one, they have provided these stations. So this particular we are having almost 450, and there are certain uh, stations wherein for one particular area data is missing. So in our climatic zonations we have not considered that station, but around we have considered around 400 stations. So with this we have prepared this particular climate zonation map. So I can share that list if you are doing any analysis. Then in that case, I can share that the data points. That data provides the data on the temperature, wet bulb temperature, dry bulb temperature, humidity, and 2 times. That is morning 8:30 and evening 5:30.
Okay, sir, and due to this global warming and urban heat island, are you considering to rezoning these climate zones?
Yes, because as we are aware that climate change is taking place, then obviously the older data wherein older data points are there. And with respect to climate change, there are new set of data which we are having now. And that is being considered. Obviously, heat island effect is the localized one. So localized one based on the local things. So we don't have any data with respect to heat, but obviously the IMD data wherein the temperature, other things are there that are being considered. And because we cannot sure that because these stations are near to airport and that particular airport may be far away from that city, and there may be heat island effect is not there, but otherwise in the other areas it may be there. So exclusively we have not considered, but in order to do the donations, we have considered this our LST, that is surface temperature we have considered, and that are the that is a the based on synthetic 1 kilometer grid, and wherein I think this particular heat island effect is being captured, and that is being used in order to do the zonation.
Okay, sir, and in the market, the people used to provide this materials with the U value mentioned on the technical sheet. Those U value is there any body to like cross check it the U value of that particular product material?
A very good question actually. And as they mentioned the value based on the steady state calculations, wherein each layer they consider the thermal conductivity, and based on that one they do calculate. So in CBRI we are having the thermal conductivity test setup. So we provide the thermal conductivity values, and for the U values, the real time U values based on the heat flux values. We do have that instruments with which real-time U value calculations are being done. But as far as the unsteady state, and for that particular thing, we are procuring one particular a bigger equipment U value test setup, wherein 3x3 wall envelope can be tested. And that setup, I think maybe within 6 months it will be ready, wherein the big walls can be the hybrid walls can be put there, and U value can be tested at any condition. So yeah, as a India, in India, that kind of facility is not there. But small facility like thermal conductivity that we can able to measure, and through that some calculations we can do, and we can get the U values.
So are you authorized to give certificate to the manufacturers?
Yes, yes, we are authorized. We can, based on the thermal conductivity and calculations, we can provide the certificate. The certificate as such, we because we do provide the testing reports, we cannot say as a certificate, but our testing report consider as a certification for that particular product.
Okay, thank you, sir.
Thank you, thank you.
Any other participants? If you have any query, you want to discuss any related idea regarding your projects, please ask the experts.
And in our CBRI, we offer internship program. So any of the students, if they wanted to come here and they wanted to do their thesis, they are welcome. Or any small little project also, if they wanted to come, they can come here. we offer this training. I think our another colleague, Dr. Tabish, I think he might have mentioned this in his speech, in his lecture, I think. So you
Yes,
all
yes,
are
sir.
welcome to CSIR in this regard. And for the project also, anything is there, you can write to us or a mail. So obviously we will reply to that one. Otherwise also you can contact over a phone. Anyway, our contact details are there with the organizing team.
Sir, how can that thermal monitoring data effectively used to retrofit old buildings for improving the energy efficiency?
Thermal monitoring data, na?
Yes, sir.
Yes, yes. Okay. So in the thermal monitoring, we can able to get an idea that what is the time lag. So herein, if we can increase the time lag, so for that increase the time lag, what we have to do is we have to provide because we cannot take out the existing layers of the wall, we have to put some additional things. So that additional layers we can put inside or maybe outside, depends on the building conditions. So wherein we can calculate what is that thickness of increase the wall thickness is required with respect to whatever material is there. If we are going with the insulating materials, obviously we have to put the outside in case of the, if we want to reduce the heat entry, then in that case we can put insulation outside. If it is a cold climatic regions, then we can put some insulating material inside the inside the surface of the wall, and we can avoid the uh, the the uh, avoid the heat losses from inside to outside. So these calculations with respect to time lag, with respect to what is the inside peak temperature, and the decrement factor, through that we can able to get an idea which kind of insulations at what thickness we need to provide it.
Yes, sir. And sir, one more thing, just in your presentation, you say that steady state thermal analysis you done. It is how different with the dynamic simulation, sir.
Yes, because here we are considering that outside temperature is constant. So maybe if we are considering that outside is maybe 40 degrees centigrade, because in case of our design also, what we can consider 40 is the maximum temperature outside, and we consider that 27, but that 13-degree difference is there, that we calculate, and based on that one we do. But the outside is fluctuating. That means 40 maybe at one particular peak time, maybe 1 hour, 2 hour, and then it is getting reduced before also and after also. So that particular fluctuation is there. That for that we need to use some kind of numerical methods, some kind of finite difference method, finite element method, and through that or time domain methods, so frequency domain methods, and with this we can able to calculate the exactly how much heat is getting transferred inside the building.
Okay, sir. Thank you, sir. So anyone, if you have any question, then otherwise we're going to conclude the sessions. So participants, if anyone has interested, so please ask the question. So thank you all for your attending insightful session on thermal monitoring and energy efficiency of buildings, delivered by Dr. Kishor S. Kulkarni, Senior Scientist at Dr. Kulkarni provides the comprehensive overview of thermal monitoring, highlights the importance of tracking thermal parameters and conducting that steady state analysis to evaluate and enhance the building energy performance. And he also discussed in detail that underline its critical role in shaping energy efficient design strategy across the different regions, that is cold region and hot regions. Sir has also thrown some light on the passive design features such as orientation, shading, insulation, and natural ventilation that contribute significantly in the thermal comfort without active energy uses. And initially, he emphasizes on the temperature monitoring in both existing and new buildings to support the data decision making for the sustainable retrofitting effects. So we sincerely thanks Dr. Kulkarni for his session and all the participants for their active participation. And we look forward to your continued participation in the upcoming sessions of this academic program. So thank you, Kulkarni sir.
Thank you very much for inviting me, and I hope I can able to contribute the things so that their knowledge can be enhanced to this. So obviously you all are welcome to CBRI. Anything is there, you can write to us through mail. We'll definitely respond to that one. Thank you.
Yes, sir. Thank you. Now we close the session. Thank you, everyone.